Welcome back to the next interesting session on the array subsystem. So in this today's session we are going to talk about the programmable logic array. So when we talk about this programmable logic array, before that we should know about a programmable logic device, because that's going to be one of the part of programmable logic device, right? And it is slightly differs from the previous memories what we have seen. So this is the main advantage over here. We can program it at number of times, right? So based on the way in which we are programming it, and based on the way in which the data can be get written and to read from your devices, we can categorize into the different categories like SPLD, a simple programmable logic device, ROM, we already know that read only memory, and PLA, programmable logic array, and PAL, programmable array logic, and GAL, generic array logic, CPLD, complex programmable logic device, and FPGA is nothing but field programmable gate array. See this how the programmable logic device are categorized. So when I say conventionally it is just categorized into two category. One is nothing but SPLD, that means simplex programmable logic device, and CPLD is nothing but complex programmable logic device. When you're going to compare these two, the architectures it's going to be a little bit differs, but the programmable logic device is going to be a common. So we are using the word called programmable logic device. What is that logic device? Let me see it in the forthcoming slide, right? So here based on the complexity of the circuits, we are just categorizing into two. One is simplex, one is nothing but the complex programmable logic device. So that's what we say is SPLD as well as the CPLD, and followed by the CPLDs can be get classified in different category. One is nothing but PROM, programmable read only memory, and PLA, programmable logic device, and PAL, programmable array logic, and GAL, generic array logic, etc. Right. So in that one we are going to talk about this PLA, right? We are going to talk about the what are the PLA's operation, right? And before that, let me have introducing the logic device, programmable logic device. What do you mean by this PLD? This PLD is indicating OR array logic, and array logic. That means the programming is possible on the PLD either by using the AND array or else by using the OR array, right? So based on how the way in which we are going to program, or how the way in which it is programmable or it is fixed, we can classify into different cadres, right? So here we can say that we can see the general block diagram how it is seems to be for the PLD. We have n input lines are available over here starting from here, and n buffer inverters are available to support the complements of the inputs, Let I write like this. These inverters are available to support the complements of the inputs. It's available over here for the purpose, and see that at the bottom and then we have this these output of these AND is nothing but the product term lines, right? And output of these OR it's going to be indicating the your sum lines, right? And the output over here is nothing but we have M output lines going to be getting available, right? So look into this table. From the table it is very clear how your PLD, programmable logic device, are framed according to category to the category. So see that for the PROM is nothing but like programmable read only memory. So where the AND arrays are fixed but the OR arrays are programmable, that means the AND arrays are not possible to program, it's fixed one, but the OR array is possible to program. Coming for the PLA, programmable logic array, where your AND arrays are fixed, AND arrays are programmable, and as well as OR arrays are programmable. Both AND and array, OR array, both are programmable. So that is what we are going to give a concentrate on this present session, and followed by we have PAL, programmable array logic, where we can see that AND array is programmable but the OR array is nothing but fixed one, and your generic array logic is almost behave like your PAL, and here also the AND array is going to be programmable but the OR array is going to be a fixed one, right. So based on the programmability of your AND and array, we can able to classify your programmable logic devices, right. See that before getting into the PLA, we can see some of the AND and OR arrays, how come it is going to be looks like before programming and after programming. See the structure over here on the before programming, you can see that there is a fuse is getting connected between your one input line to the your AND array. See that the AND output of this AND array is nothing but A, B, C, D before programming it. So before programming, in the sense the fuse are not blown. The fuse are not blown in the sense whatever available on the A, B, C, D is going to be getting available at the AND logic. Accordingly, we can say that A, B, C, D is going to be the output of your AND logic. See that after the programming, what is the meaning? Here the fuse are blown, here the fuse are blown, that means here the logic is 0, here the logic is 0, that means this is not going to be feed as an input for this. The input between this A and the AND is got disconnected. That's the meaning. It doesn't mean that logic 0, okay, it doesn't mean that logic 0, here the fuse are blown, because during the time of programming the fuse are blown, that means there is no connectivity is going to presence between this line to this line, nothing is available. That means the previously before programming it was the output of this AND gate is ABCD, but now since the A is not connected with the AND gate and D is not connected with the AND gate due to the fuse blown, now we can see that the output of your AND is nothing but BC. So this is what we can say that your AND array is getting programmed, a programmable AND array we can say. Same way we can see for the OR gate on the left hand side over here, you can check out on the left hand side. See that before programming how it is going to be available for the OR gate, since the OR gate operation is going to be addition operations, we can say A plus B plus C. And how come we can able to represent before programming, it's represented by means of the star symbol. Can you able to see that? If anything is going to be allocated with the star symbol, it means that the fuse is present. That means the input is accessing, that your OR gate is your input is access to the OR gate, so that we can say that the star is present. And see that what is the change we are seeing after programming. You can see at the point of C, the C is getting disconnected from the OR gate because the fuse is got blown. So we can see the output part that after programming we can see that is similar to the array logic what you are going to discuss it over here. There is no star element is not present over here. It means that where we can say 0, so here the logic is going to be 1 1 0, that we are providing, so the output is going to be A plus B, right. Same way when we talk about here on the AND gate programming, AND programming on the right hand side over here, and until before programming it, its fuse is going to be getting available, we can say that ABC is going to present, all star is present, so that we can say ABC. And here what we can able to see that the fuses get blown, so the C is not connected, so this line indicating that the C is not connected, so there is no meaning of 0, the C is not connected over here, the output is become AB. So that is a way in which we can able to do the before programming of array logics like AND array logic or OR array logic, and after programming of your AND array logic and the OR array logic, how it is going to be getting differs in terms of the operations, right. See here we are talking about 32 cross 8 ROM. You may remember the ROM structure is nothing but what, M cross N, that means it having the 32 words. M is equal to 32, that means it having the 32 words, you may remember from the previous session. And what about this N? N is nothing but what? N is equal to 8, 8 in the sense what is the meaning? We have 8 bits. That means if I take a word, one word, it consists of 8 bits. Okay, 1, 2, 3, 4, 5, 6, 7 and 8. So like this I am keeping word 1 until I will have word 32. Sorry, word 32, I will have the same of 8 bits like this. 1, 2, 3, 4, 5, 6, 7 and 8. So it's using M32, that means 32 words and 8 bits. And also you may remember how we can write this external structure. External structure can be written as 2 power k cross n. I hope you may remember. That is the external structure view we can say. And what about the internal view? We can say internal view we can write the decoder in such a way that we can write k cross m is the internal decoder view. So what is a k cross m? K cross is m. K is nothing but what? Since it is 32, 32 is equal to 2 power 5. So we can say k is equal to 5. So I will rewrite it over here. Okay, I hope you can able to understand. Right? Yes. So we have 32 cross 8. So m is equal to 32 and n is equal to 8 because we know that it's going to be m cross n structure. So we have 32 words. We have 8 bits per word. That is the meaning. How we can draw the external structure? External structure can be drawn by means of 2k cross n. So what is k over here? K is nothing but, now what is the k over here? We can write, since it is m is 32, so we can say it's 2 power 5 cross n will be the k. Because how we can gather this 32? That is what we are doing over here. Right. So now what we can write k cross m. So we can write k cross m. So k is nothing but 5 cross, what is m now? M is nothing but 32. So we can say 5 cross m, 5 cross 32 decoder is going to be needed for us. That is what it is present available over here. So since we need only the 5 input and 32 decoding line is going to be getting available. So we can see that I0 to I4 is going to be given as an input over here. I0 to I4. So I0, I1, I2, I3, I4 is going to be provided as an input over here, and followed by we will have an enable line will be getting available. Right, and output is going to be like 8 bits of words. We for per word, how many bits we have? 8 bits. So we can see that A0 to A7 going to be present at the output side over there. Right. See that how come it's going to be getting available? A0 to A7 is going to be getting available as like the previous one we are writing it. Let's say for example we are keeping this, that means like 0 0 0. What is the output we should require? The output must be required as 1 0 1 0 1 1. That means we can take this as an output for your particular things, we can say for your A7. Correct. So for A7 we can say this is going to be your we can say like this is going to be the things we can take it out for a particular things. For example, see, for every one in truth table specify the closed circuit, of course. Okay, so before getting into this, let's see this one, because then you can able to understand very easily. See that before understanding the logic, what is it available inside? How come the programming can be done on your structure, internal structure? You can see that wherever star is available, it's meaning that there is a connectivity. So what does it mean here? According to the first condition 0 0 0, we have like 1 0 1 1 0 here. Check out this structure. Okay, we have 1, so we made it as a star here. This is 0, this is 1 now, this is indicating 0, now it is indicating 1, this is indicating 1, this is indicating 0, this is indicating 1 1, this is also indicating 0. So that is the way in which we can able to program it over here. We are just programming it, because right, that's what we are doing it over here. And when every 0 is nothing in truth table specify that is going to be a open circuit. Right. For example, if you are going to provide the address, what is the address of the 000 111? Like for example, where it is available 000 111. Okay, 000 111 somewhere it's going to be available over here. 000. Oh, sorry, 0011. It is not 000 111. 00 yeah, 00011. Yeah, 00011 is the address we can have. So 00011 is nothing but where the 00011 is available. This will be the 00011. This will be the 00011 is going to be getting available for the respective output. What is it stored is going to be taken as output at the end point over here. That's what we can able to witness from the table there. So now you see the PLA. What we seen in the PLA, both your R plane and as well as the AND plane is nothing but programmable. And as well as here we have X1, Xn to Xn is available as for the input buffer, and followed by we have the AND plane, that is programmable connection is possible, and in your R plane also the programmable plane coordinate connection is going to be getting possible over there in the PLA architectures. Right. So followed by, let's see that we are going to implement some of the functionality on your PLA. How come? Let's see that. See the what is the functionality of f naught? F naught is nothing but a plus b bar c bar. F1 is nothing but ac plus ab, and not ac bar plus ab. This is a plus b bar c bar. F1 is nothing but ac bar plus ab, and F2 is nothing but b bar plus c bar, b bar c bar plus ab, and F3 is nothing but b bar c plus a. That is what the things going to be getting available. Now before getting into it, you just see the input side and you must understand the output side. So what is the input side? When I say 1, it is asserted in terms of, that means if 1 is in the sense that is going to be asserted, that means it is connected. And when you say the 0, it indicating it is going to be a negated. Okay, and when there is a dash symbol is going to be available, it is not participating in the programmable part. And the same way on the output side, when I say 1, that is term is connected to the output. When I say 0, there is nothing is going to be connected to the output. That we have to be understand. Now you see that the personality table of the particular function what you want to implement. In that one you can say the 3 parts. The part 1, this is going to be a part 2, this is going to be part 3. So part 1, what is it available? That is nothing but the product term. So before filling the column 2 and column 3, so in column 1 we have a product term, and column 2 you have a input terms where how many variables are available here? A, B, C. So we can say A, B, C, 3 terms are available, and the output terms is nothing but we need a 4 functions. So F0, F1, F2 and F3, right. Now first you fill your product term. What are the product terms that are involving on the functionality? What else is available? A, right, and AB, A C bar, B bar C bar, B bar C. So that is what available in terms of across F0 to F3, right. So now we move forward to the input terms. How come the input term is going to be getting available? So since A is available, we are writing A is equal to A1, and there is no B, there is no C, I am writing minus. That means I am keeping hyphen, nothing is available. As like what we are input, we are asserting it. 1 means asserting it, 0 means we are keeping negation. That means we are going to take a negation of it, and hyphen says that it's not going to be getting participating it actually. So now for AB what I am writing? So I am writing AB, A is available, so I am writing 1, B is available, I am writing 1, and there is no C, I am writing dash. Nothing is not available there. Now we have AC bar, so A is available, B is not available, so we can make a dash, and C is not available, we need C bar, so we can make it C bar as 0. It indicating that we are connecting C bar not with C, because we initially we seen that there will be a supported by your NOT gate. So if this is going to be C, if this is going to be C, this is going to be a C bar. So now we are going to make 0. It's meaning that I have to take a input from, I have to take a input from here. That means to the next array of logic over there, right? Right. Then next one, right, B bar and C bar. That means A is not available, I am putting dash. So what does it mean B bar? So it's not B, it's B bar. So we can write 0. So it's not C, it is C bar. I will write 0 for this. Same way we can write for B bar C, like hyphen 0 1. Now how come the functionality can be returned? Let's say for example, so now what is the functionality return? Let's say for example for F naught. What is the functionality F naught? F naught is equal to A bar, A plus B bar C bar. We should not here, we should not show in terms of the, we should not see in terms of row wise, we should not see in terms of the row wise, not possible, we should see in terms of the column wise. Okay. So how come we can write now A is equal to A plus B bar C bar. Where is available A? A is available here. And where is B bar C bar is available? B bar C bar is available. If we take output of here, this can be a F naught. You can see that, right? We have F naught is equal to A plus, here we can say it's going to be A plus B bar C bar is available. F naught is equal to A plus B bar C bar, right? Same way come down to the F1. So what is F1 is available? F1 expression is nothing but AC bar plus AB. Where is AC bar is available? We can say AC bar plus AB is going to be getting available. That is going to be a F1 output. So we can say that here F1 is equal to AC bar plus AB is going to be getting available. I hope now you can able to fill your F2. What is F2 is going to be? F2 is nothing but B bar C bar plus AB. So B bar C bar plus AB is going to be getting available, followed by F1 is nothing but what is say, like B bar C bar A, B bar C is going to be available. So F3 is equal to A plus B bar C is going to be available. So we can able to implement in simple way like this, right? So as like the previous that is what I am just looking the table. You can look the table again how it is going to be. That's what we seen in the previous slide. Now we should convert that into a logic diagram. We have to convert this into a logic diagram. How we can convert? See the logic diagram how it is going to be getting available for F0. What is the meaning of F0? F0 is nothing but what? A is equal to A plus B bar C bar. See that where it is available, we have A, we can make a cross point. A is connected for the OR logic, programmable, and same way we have to connect with the B bar C bar. So first see that where the connectivity is going to get taken. This is should be taken from here. This is taken from here. It's going to be A. Okay, this is going to be A, and this is going to be get connected over here, B bar C bar. So where is B bar available? Here we have B bar available, and the point here is C bar. So it's providing B bar C bar. I can make a cross connections over here. Right, so this no connectivity because this line is not connected anywhere over there. So we can make it right. And same way when you talk about the F1, what is F1 says? F1 says that AC plus, okay, AC bar, right? This is AC bar plus AB. So we can say that F1 is nothing but AC bar plus AB, because AB we are connecting from here. This is going to be A and this is going to be B. So AB is get connected over here. Same way here we have AC bar. So we can just make it as A and C bar. So we can say A and C bar is going to be getting available like this. So like that we can able to complete the entire structure of your PLA, right? So we should remember that how we can able to fill the personality table. From the personality table only we can able to recreate the structure of your PLA device, how it is going to be getting programmed, right? So I believe it's given a clear picture about the PLA operation and how it is going to be getting structured on your array logic, your AND array logic, and as well as the OR array logic, right? Thank you so much.